Hello friends. Okay, so we are live and today we are here with the Euler Totient function and welcome to my channel Maths Corner. So my name is Saman Bitlia. So let us start with Euler Totient function. Let me see if the voice is clear or not. Okay, so let us start with Euler Totient functions in calculating the number of co-prime numbers which are of some numbers. Okay, so let us start with Euler Totient function. So first of all, fire function and it counts the number of positive integers less. So let us try with an example. Suppose we have to calculate the value of phi of 15. So what is the value of phi of 15? I will give you some time to calculate the value of phi of 15. Okay, so phi of 15, what's actually the meaning of phi of 15? All the natural numbers m such that m comma n. So let me find out all the 8 is co-prime to 15, which are co-prime to 15. So I have the value. Okay, so calculating phi n for large n is not easy and it is time consuming. So we develop a method of calculating phi n. So now we have developed some inductions. We have developed some formula to calculate phi n for very large number in a seconds. So let us see. We will also derive that formula in this video. So let us start. Before moving to that thing, let me give you an idea of the multiplicative property of totient function. Okay, so let me give you the idea of multiplicative property of totient function. So the multiplicative property says that phi of AB is equals to phi of A into phi of B, where GCD of A comma B is 1. Okay, so this is the property says that. So this is the phi of AB. This is the multiplicative property. Okay, so let us see. First, let us see that by giving an example. First of all, let us say I want to calculate phi of 15. So I can write down 15 as 5 times 3. So this will be phi of 5 times 3. Now here A is 5 and B is 3 and also GCD of 5 comma 3 is 1. So I can write down this as phi of 5 into 3 as phi of 5 into phi of 3. Phi of 5 into phi of 3. Now what is phi of 5? Number of numbers which are less than 5 in a co-prime to 5. After calculating it will come out to be 4 and 1 2 3 4 or there are 4 numbers that are co-prime to 5 and this is phi of 3. After calculating 1 2 will be the numbers which are co-prime to 3. 4 times 2 which comes out to be 8. So what is 8? This 8 is my phi of 5 into 3 and what is this? This is phi of 15. So I get the value of phi of 15 to be, so I get the value of phi of 15 to be 8. Now let me calculate this by the physical method, that by counting method that we have learned before. Okay, so what will be my phi of 15? My phi of 15 will be the number of numbers which are less than 15 and co-prime to 15. So let us try with phi of 15. So phi of 15, what are the numbers which are co-prime to 15? 1 is co-prime to 15, 2 is co-prime to 15, then 4 is co-prime to 15, then 7 is co-prime, and then 11 is co-prime to 15, and then 13 is co-prime to 15 and 14 is also co-prime to 15. And what else have left? And one more number is left, which is 11 12 13 14. So we get 1 2 4 7 11 13 14, and then one more number is left which is 8. So these are the 8 numbers which are co-prime to 15, and this is the same as the result we got before, which is 8. Okay, so we get phi of 15 is 8. So the totient function is multiplicative, where phi of AB is equals to phi of the multiplicative property of totient function. Now, so after knowing this, we can start with our the proof of formula for calculating phi n. So computing phi n. I am reminding again that if you have not yet subscribed my channel Maths Corner, you have to subscribe and hit the bell icon just right now. Okay, now I will calculate phi of n. First of all, let me assume that n is a number, and after doing its prime factorization, I got p1 to the power alpha 1, p2 to the power alpha 2, p3 to the power alpha 3, and so on till pn to the power alpha n. So this is just the prime factorization of n that I got. And after writing the prime factorization of n, it's forms something like this. Okay, now what will be my phi of n? My phi of n will be phi of p1 power alpha 1, p2 power alpha 2, all this thing. So phi of p1 power alpha 1 into p2 power alpha 2, and so on till pn power alpha n. Now as all these n factors, all these n prime numbers are co-prime to each other, so I can break them as each phi. I can break down them in each phi. So this will become phi of p1 power alpha 1 into phi of p2 power alpha 2, and so on till phi of pn power alpha n. Okay, now I have my now goal is to calculate phi of some prime number to the power alpha. Okay, now my goal is to calculate phi of some prime number, let's say p to the power any number, let's say alpha. Now what is this? There are a number of numbers which are co-prime to p to the power alpha and are less than p to the power alpha. Okay, when I calculate this, first of all, I will write down the total numbers which are less than or equals to p to the power alpha, which will be p to the power alpha only. And the number of for example, if I have to find out the number of numbers which are less than 5, these are 5 only, 1 2 3 4 5. Similarly, the number of numbers which are less than p to the power alpha will be p to the power alpha, and from this I will subtract all the numbers. From this I will subtract all the numbers which are not co-prime, to p to the power alpha, or which are factors of p to the power alpha. So I will subtract here all the numbers, all numbers which are not co-prime with p to the power alpha, with p to the power alpha. So I will subtract this the number of numbers which are not co-prime to p to the power alpha. This is a principle of inclusion and exclusion, and it's very basic thing. So total minus not co-prime will give me the number of co-primes. So let me write down all the numbers which are not co-prime. That is the number of factors of p to the power alpha. Also, okay, I can't say the number of factors. Let us find down what is p to the power alpha. How many numbers are there of p to the power alpha less than equals to p to the power alpha such that the GCD with p to the power alpha is not equal to 1. So first thing, let me calculate 1 into p, and second is 2 times p. These are the numbers which are not co-prime to p to the power alpha. Then 3 times p, 3 times p, and then 4 times p, and so on till p to the power alpha minus 1 into p to the power alpha into p, simply p. Okay, so this will become p to the power alpha minus 1 plus 1, which is p to the power alpha. So these are the all the numbers which are not co-prime to p to the power alpha. So these are all the numbers. So how many numbers are there? Which is 1. It is the p is multiplied with 1. Here p is multiplied with 2. P is multiplied with 3, and so on till p is multiplied with p to the power alpha minus 1. So take total, there are p to the power alpha minus 1 numbers. Total, there are p to the power alpha minus 1 numbers which are not co-prime to p to the power alpha. So total minus not co-prime will give me the co-prime. So I get phi of p to the power alpha will be equals to phi of p to the power alpha will be equals to p to the power alpha minus p to the power alpha minus 1. Now from here I will take p to the power alpha minus 1 as common, and here I get p minus 1. So this is my value of phi of p to the power alpha. So I get phi of p to the power alpha is equals to p to the power alpha minus 1 into p minus 1. So this result I will use in my this thing. Now what will be my phi of p1 to the power alpha 1? This will my this will be my I will use this thing p1 to the power alpha 1 minus 1 into p1 minus 1. This will become p1 to the power alpha 1 minus 1 into p1 minus 1 into p1 minus 1 into p to the power alpha 2 minus 1 into p2 minus 1 into p2 minus 1, and so on, so on, so on, till, and what last I will get 5 of pn to the power alpha n. It will become pn to the power alpha n minus 1 into pn minus 1. Okay, so this will be my phi of n. This will be my phi of n. Now I will write down this p1 to the power alpha 1 minus 1. I can write down this as p1 to the power alpha by p1. This is a law of exponent, and I will do the same thing here, and I will combine the all. I will combine this thing, this thing, this thing after writing this in this form. So after arranging and rearranging, what will we get? We get phi of n. Phi of n will be p1 to the power alpha 1 by p1 into p2 to the power alpha 2 by p2 until pn to the power alpha n by pn into I will get 1 minus p1, 1 minus p2, so on so on till 1 minus pn. So this is my phi of n that I have calculated. This is my phi of n. Now I will do one thing. I will transfer the p1 in the denominator with with a division of this thing. So and this thing p2 will be transferred here, and similarly p3 will be transferred next time, and pn will be transferred here. So this my phi of n will becomes, now this denominators are removed and transferred there, so this will may become power alpha 1 p2 to the power alpha 2 till pn to the power alpha n into 1 minus p1 by p1. This will become 1 minus p1 by p1, which will be 1 minus 1 by p1. 1 minus 1 by p1. Okay, 1 minus 1 by p1. Now when I transfer this here, I will get 1 minus p1. Let me see, p minus 1. So it's not 1 minus p1, it is p1 minus 1. p1 minus 1, and this thing is p2 minus 1, and so on till pn minus 1. Now I will transfer there to p1 into 1 minus 1 by p2, 1 minus 1 by p2, and so on till 1 minus 1 by pn. Okay, so this is my value of phi of n. Phi of n now bigger. Now when we observe this thing, we get p1 to the power alpha 1, p to the power alpha 2, to pn to the power alpha n. This thing is equals to n only. This thing is equals to n only because I have assumed n to be this only. Assume n to be this only. So when I calculated, I get the value of phi n in terms of n. So this is my n, and p1 1 minus 1 by p2 till 1 minus 1 by pn, where p1 p2 p3 pn are the distinct prime factors of n. So what we get is, so we get is, let me write down. So we get phi of n will be equals to n times 1 minus 1 by p1 into 1 minus 1 by p1 into this thing is that GCD can remove the multiple of another number, a number from the another number. We can also write down this as a, which is also equals to GCD of, using this fact I will use this. So what will be GCD of 100? What will be GCD of 100? 1 comma 100. This will be, now here I will take lambda as 1. So this will be my GCD of a minus lambda as 1. So a minus b. So 100 1 minus 100 which will become 1 comma 100. Okay, so the thing that I've got is GCD of 101 comma 100 is GCD of 1 comma 100. Similarly, I will get GCD of 102 comma 100 is GCD of 2 comma 100. So the number of numbers which are co-prime to 100 in this set will be equal to number of numbers which are co-prime to 100 in this set. So here also 40 numbers are there which are co-prime to 100. So when I do the 40 plus 40, which comes out to be 80. So there are 80 numbers total in this set which are co-prime to 100. So answer to this question should be, let us move to Euler's theorem. Now it's a very good application of Euler Totient function, and you must know some basic concepts of model arithmetic before moving to Euler's theorem. Okay, so let us start with this. So Euler's theorem states that a raised to power phi n is congruent to 1 mod n provided that GCD of a comma n is equals to 1. Now GCD of a comma n is equals to 1. Now a raised to power phi n is equals to 1 is congruent to 1 mod n, where phi n is the Euler Totient function. Now it's a very good theorem that leads to me some questions of modular arithmetic. Now let us try with an example. GCD of a comma n is 1. So when I take a as, let's say a is 7 and n is 2, n is 2, or I can take let's say a is 2 and n is 7. I'm taking a is 2 and n is 7. So when I calculated this, I substitute the values there. So a to the power 5n, this will become a is to 2 to the power 5 of 7. This thing is congruent to 1 mod and n is by 7. Now according to this Euler's theorem, this should be true. Let's see if it's true or not. Now what is 5 of 7? I have 5 of 7 will be 6. The one thing that you need to remember is phi of any prime number phi of any prime number is equals to prime number minus 1, prime number minus 1. So all the numbers which are less than, when I can also prove this using a formula, let's say phi of prime number p, it will become number itself p into what are its factors. It's only 1 minus 1 by p only, so it will become p minus 1. So phi of any prime number is prime number minus 1. Okay, so what will be my phi of 7? As 7 is a prime number, so it will become 2 to the power phi of 7, which will be 6, and this should be congruent to 1 mod 7. Okay, now what is 2 to the power 6 is 64, and which is congruent to 1 mod 7. Yes, it is also true that when 64 divided by 7, the remainder is 1 only. So this Euler's theorem is applicable everywhere, provided that GCD of a comma n is 1. So now let us try with an example. Now the question is asking me that I have to find out the last three digits of 13 to the power 9999. Okay, so the thing that you remember is the last three digits are the number mod 1000. Okay, the last three digit is the number mod 1000. What are last two digits? Last two digits is number mod 100. Last digit is number mod 10. So the last three digit is number mod 1000. So I have to basically find out 13 to the power 9999 is congruent to how much mod 1000. Now I will start with Euler Totient function. I will start this question with Euler Totient function. Now as GCD of 13 and 1000 is 1, so I can write down that 13 to the power 5 of 1000 should be congruent to 1 mod 1000. This is my Euler theorem. It's congruent to 1 mod 1000. Now what is my 5 of 1000? 5 of 1000, I can write down 5 of 1000. When I calculated this using the formula that I have before calculated, this will comes out to be 400. 5 of 1000 will be comes out to be 400. So this will become 13 to the power 400 is congruent to 1 mod 1000. Now I will raise the power of both sides by 250. I will raise both powers by 250, or I will raise the power with 250. Now from here what I will get 100 into, now let me raise the power with 25 only. So when I raise the whole power with 25, this will become 1 raised to power 25. So what is my 25 into 400? It will become 10,000. It will become 10,000. Okay, so I get 13 to the power 400 into 25, which is 10,000, is congruent to 1 raised to power 25, which is 1 mod 1000. But I have to calculate 13 to the power 9999, so I have to remove 113 from here. So I will do one thing. I will again use the property of modular arithmetic that if we have any number, let's say if a is congruent to b mod m, if a is congruent to b mod m, then I can add the multiple of any multiple of m to the b to the right hand side. So if this is true, then a should also be congruent to b plus some multiple of m mod m. So I will here also I will use this property. Here also I will use this property. So I will add a multiple of 1000. I can add a multiple of 1000 to 1 such that this 113 can get cancelled out. So I will here I will add 13 to the power 1000. This thing will be congruent, 10,000 will be congruent to 1 plus I will add a 1000 only, which is a multiple of 1000. 1 plus 1000 mod 1000. Now what is my 1 plus 1000? This is my 1001. This is my 1001. Now when I want to cancel it out, 113 I can cancel it out, as the GCD 13 comma 1000 is 1, so I can cancel out the common factor. So I am cancelling 30 on both sides, this by 30, this by 13. So with 13 raised to power 10,000 divided by 13 will be 13 raised to power 9,999. This thing is congruent to 1001 by 13. It comes out to be 77 mod 1000. So I get the last three digits are 077. It means 077. So last three digits of this number is 077. So this was a very good application of Euler's theorem. Okay, so this is all for today. Thanks for watching my video, and don't forget to like, subscribe and share this video, and subscribe my channel Maths Corner to get access to the practice problems of today's lecture. And if you subscribe my channel, I will post in the description the practice problems for Euler Totient function. So that's all for today. Thanks.